In this next section, we're going to talk about thermochemistry and thermodynamics, which is chapter 5 and 19. It's interesting that our book kind of has them on completely opposite sides of the book, but they are very much related, and understanding chapter 19 will help make some of the upcoming topics more understandable. So, thermochemistry is the study of chemical reactions and the energy change that it involves heat. Thermodynamics, on the other hand, is the study of energy and how it can transform into different types of energy. So we'll talk about that towards the end of the chapter. So thermochemistry is chapter 5 and thermodynamics is chapter 19. We're going to start by the first law of thermodynamics, and this is actually chapter 5.2. That says that energy can be converted from one form to another, but you cannot destroy it or create it. So whatever energy is out there right now is what we have, and you can't get more and you can't get less. So when we want to heat our home, we're converting chemical energy when we burn fuels to get it into heat that gets released. Sunlight is a type of energy that gets converted into chemical energy, right, as sugars when plants do photosynthesis. And so those show how energy also gets transformed, right? So thermodynamics. So some transformation happens there. When we start talking about energy, it can get a little complicated because energy moves from one space to another. And so we want to keep in mind what we're talking about. So the first thing we'll talk about is defining something called the system. The system is the thing in the universe that we're studying. So if we're looking at this piston right here that has some gases inside of it, the gases inside, these are the system. We often think about the system as the reaction that's occurring. An open system happens when both heat and mass can leave, basically. So if this piston didn't have a top on it, then I could have those gas molecules can leave, so mass leaves, as well as if a chemical reaction is happening, the energy involved in that could also leave. A closed system happens when you only have heat that gets exchanged, but the mass stays in. So this would be like if you had a coffee cup, right, that had a lid on it. It's not like over time that coffee is going to cool down, so the heat can escape, but the coffee stays inside. An isolated system happens when both heat and mass cannot leave and escape to the surroundings, so they're trapped inside. If we look at this image here, then the system is the gas inside that we're studying, but the surroundings are everything outside. So both the piston here and everything outside of it. So when we think of a chemical reaction that's happening, oftentimes we're measuring it, right? So if I put my hand right here, right, and I feel energy, maybe it gets hot. So energy is leaving, and I'm feeling that warm my body is the surroundings. So oftentimes it's hard to distinguish because we're so like ego focused that we kind of feel like we're the system, but we are the surroundings. And we're making observations about the system or the chemical reaction. Now we're going to define something called internal energy, which is the sum of all of the potential energy and kinetic energy within a system. So potential energy could be, right, the height of it when we think about physics, right, how high it is and how much it could fall, but it also has to do with chemical bonds that are stored in there. And then kinetic energy is anything related to movement. So whether the particles are moving or vibrating, it could be the heat involved with it or light energy. So that both of those are included when we think about internal energy. We just represent it with the letter E, and generally we don't actually know E at a given point, but we only know how it changes, or delta E. So here, if I have a reaction happening, initially I'm hydrogen and oxygen, like I saw in that piston, chemical reaction happens, and my energy goes down, and then there is a change in energy that I can measure. And usually the way we're measuring that is with both the heat involved as well as the work. So the reaction, or the equation you need to know, is delta E, the change in internal energy, equals the heat involved in that reaction plus the work. And work is a little bit trickier to think about because heat, we know heat, right? We feel warm, we feel cold, we can think about heat more tangibly, but work has to be done oftentimes with a gas in chemical reactions. It's a little bit different than when we're talking about, if I'm going to do work and I'm pushing a force over a distance. That is true because work equals force times the distance that it's applied. But in this case, we're not going to think about that in that way. We're going to actually think of it for gases, which is work equals negative pressure times the change in volume. So let's talk about what work looks like when we're thinking about gases. So if I had a table, I would know that I'm pushing on the table with this much force over this certain distance that it traveled. So that's a little bit more straightforward. But when we're talking about gases, there's a positive and negative sign associated with it. But you can think about it in the sense of, here I have a gas inside, right? That's our system. So we need to think, is our gas doing work, or are the surroundings doing work? So if we think about, is the gas doing work? Well, that would mean that the gas is pushing out onto the surroundings, in this case, this movable piston, and the volume is going up. So if my gas is doing work, then we know that my change in volume is positive. It went up. So then when I plug into my equation, work equals negative force times change in volume, here being positive, I have a negative times a positive, is going to equal a negative. So when I have negative work, that means that work is being done by the system, or in this case, by our gas. If work is being done on the system, well, that's kind of like the surroundings are doing work. So work being done on the system means the system is being pushed on. The volume is actually decreasing. So we'd have work equals negative, that shouldn't be force, that should be pressure. Should be pressure times negative volume, because the surroundings did work and my volume decreased. And so the work is positive. So when I have positive work, work is done on the system by the surroundings. So we could even say that, by surroundings. So that's work. So hopefully that little tutorial kind of made sense about the signs of work. Is it being done on or by the system? Again, by the system means the system's pushing. On the system means the surroundings are pushing. We already are pretty familiar with heat. If I add heat, then the system is going to get hotter, or it's going to gain the heat. If the system loses the heat, it's going to get cooler, right? So gain and lose, positive, negative, that makes sense. And then we add these two together, add the heat and the work together to give us the total energy value. And that will tell us, did the system gain energy or did it have a net loss of energy? So let's practice. We have two gases in our cylinder piston arrangement, and there's two gases and they form a solid product C. As the reaction occurs, the system loses 1150 joules of heat to the surroundings. The piston moves downward as the gases form a solid, and the volume of the gas decreases. And there is 480 joules of work involved. It says the surroundings did it, which makes sense, right? The volume went down because the surroundings are pushing on them. So what's the change in internal energy? So we're going to go here and think E equals Q plus W. And the key thing is here, we know the numbers, but we just need to think about the signs. So we'll do E equals, we know the heat value here is 1150 joules, And it said that the system lost that much heat. So when we're thinking about our system, if it lost the heat, then that is a negative sign for the heat. Now we're going to put plus W. And then it says that the surroundings did 480 joules of work, right, because the volume decreased. So I would like you to get in the habit of using the work equation, negative pressure times change in volume, to figure out the sign. So we know that it's negative P times the volume went down, so times a negative. So negative times negative equals a positive value. So we have a positive 480 joules involved. So when we calculate that out, we measure negative 1150 joules plus 480 equals negative 670 joules. Okay, we have another one here. I would like you to pause and try this one on your own if you haven't gotten that habit yet. But we're going to calculate the change in energy for a process which the system absorbs 140 joules of heat from the surroundings, and the system does 85 joules of work on the surroundings. So the system now is doing the work. So let's do our calculation. We have energy equals Q plus W. We'll look at each of those separately. So the heat, the system is absorbing, so that means it's adding it in. So positive 140 joules plus, and now we have work equals negative pressure times volume, change in volume. And the system did work, which if we think about our piston, the gas inside, the system's doing work. So the gas is pushing up, and we're going to increase that volume. So we're going to have times a positive change in volume. So we'll have a negative sign here. So plus negative 85 joules. And you can go look at the chart just to double check, but I do want you to get in the habit of like conceptualizing in your brain what this means. So we're going to do 140 minus 85, and we get 55 joules. All right, now we're going to talk about more of a calculation one. So we have a fuel burning in a cylinder that has a piston. It emits 430.5 joules of heat. The volume of the cylinder is, it starts at, I'll just kind of do a little picture, 0.250 liters, and the final volume is 0.98, so we know it went up. If the piston expands against a constant pressure, you know the pressure here is 1.35 atmospheres. What's the change in internal energy? And then they give us a conversion factor we're going to use in a minute. So let's practice. We have our equation. We want to know the internal energy. So E, let's actually change in E, equals Q plus W. Now they give us Q, right? So emits, so that means a negative, so negative 430.5 joules. But they don't just give us the work value like they did before. We actually need to calculate it, which maybe actually is easier because we have the signs that will be calculated rather than kind of conceptualized. So we'll have negative pressure times change in volume. So we'll do negative, our pressure is 1.35 atmospheres, and our change in volume is going to be final minus initial. So it ended at 0.98 liters, and it started at 0.25 liters. So we're going to calculate that, and we end up getting, so if we multiply this all out together, the work we get is equal to negative 0.9855, and the units are atmospheres times liters. Kind of a weird one. It's a combo unit, just like density, which is like grams per liter or grams per milliliter. This is atmosphere time liter. That's fine. But we have our energy in joules, so we can't have our work in atmosphere liters. We actually need to convert it to joules. So It's going to do a quick little conversion factor. We want to get out of atmosphere liters and into joules. We can use our conversion factor that says 1 liter atmosphere equals 101.3 joules. Do that calculation and we get, and don't forget the negative sign here, my bad, is negative 99.8 joules. So now we can plug that in. So we have negative 430.5 plus the negative 99.8 joules. Add those together and we get negative 530.3 joules. This next section for chapter 5.3 is studying enthalpy. So enthalpy is a common term that we will use rather than energy. It's more widely studied and reported on. And it basically gets used when a process or a reaction takes place at constant pressure. We only have pressure volume work happening, and so we can account for the heat flow through this enthalpy value, and it's the letter H. And you'll see why it actually ends up, I believe it used to stand for the heat, and you'll see why in a second. So H, just its pure value, is equal to the internal energy plus pressure times volume. So, but when we are at, again, constant pressure, then the change in enthalpy actually starts to break down. So just like energy, enthalpy is often measured by its change, not its value at a given point. And so what we're going to do is we're going to derive the value of enthalpy at constant pressure. So what we do is we take our delta H, so we're adding a delta here. Now we're going to apply the delta in. When we do this, it's not as simple as with traditional algebra. We actually say we apply the delta in and we do delta E plus pressure times delta V. So we're going to apply the delta to the P and the V. So here I applied it to the V, and then I'm going to do plus pressure, delta pressure times V. We do know that we are at constant pressure, so there shouldn't be any change, so that one just goes away, which is nice. So we have our enthalpy is change in energy plus pressure times change in volume. But now we're going to actually break down the energy term. We know that energy is equal to heat plus work, which we're also going to break up work. Remember, work is negative pressure times change in volume. So we end up getting here that delta H equals heat here plus or minus pressure times change in volume plus pressure times change in volume. And hopefully you can see that these terms both cancel, and we get that at constant pressure, the enthalpy is just equal to the heat, which I believe is why it has the letter H instead of like a different term. This is a pretty valid approximation because if you think about when you do a reaction, maybe you do like the vinegar baking soda experiment where it gets all bubbly, gases get released there, but they open up to the atmosphere, and while the pressure technically would have gone up, it would be so significant because our atmosphere isn't going to change by that much based off of a simple reaction that you did. So we consider a process to be endothermic when the enthalpy value is positive, and a process is exothermic when the process is negative. So again, if heat goes into the system, it's endothermic. If heat leaves the system, it becomes exothermic. For chapter 5.4, we're going to talk about the enthalpy of a reaction. So we know that enthalpy, right, we're going to be measuring change in enthalpy just like we did change of internal energy. And it is final minus initial. Right, so change of enthalpy is going to be the enthalpy final minus the enthalpy initial. But in a chemical reaction, the final thing is the products and the initial thing is the reactant. So what we actually are going to write for chemistry is that delta H equals enthalpy of my products minus enthalpy of my reactants. and we'll actually notate it, calling it delta H reaction, meaning the enthalpy of the reaction. So if I have a chemical reaction where I have these two reactants that are reacting and there's an explosion, we know that it felt hot, so heat exited the system. So the enthalpy of our products is lower than the enthalpy of our reactants that we started with. So it is an exothermic reaction because the heat or the enthalpy amount went down or dropped. It exited the system. So some of the properties that we want to keep in mind of enthalpies that will come in handy later is that enthalpy is an extensive process, which means it matters how much matter you have. So it is amount dependent, meaning that if I have a small amount of gasoline, like a little tiny beaker full versus a big jug, so I have this tiny little beaker of gasoline and then I have this huge tub of gasoline and I set them both on fire and a chemical reaction happens, we know that this one's going to release a huge amount of heat energy because there's just so much more of it. So enthalpy is amount dependent or extensive. And then also enthalpy change for a reaction is the same number but the opposite sign if we go in the reverse direction. So for example, if I have methane and oxygen reacting to form carbon dioxide and water, that's a combustion reaction. It releases heat, so that goes down. But if I tried to do the opposite reaction, I'm going to have to, it's endothermic to the same amount. So we could just switch the signs when I flip the reaction. And then we also want to keep in mind that it does depend on the state of the reactant. So if I was dealing with water that was gaseous here, I'm going to have a different value for enthalpy because this value that is listed right there depends on the phases or the states of the reactants and products in the reaction. If they're not in the way that it's written, the value is going to be different. So let's practice. We had that reaction before. Here it is. Right here, this reaction we're going to refer to. How much heat is released when 4.5 grams of methane is burned in constant pressure. So we have our methane, CH4, being burned in oxygen, and it's going to make carbon dioxide and water, and our coefficients are 2 oxygens and 2 waters. And pause real quick. Okay, I just want to move that over so then I could also write that the delta H of this process is negative 890 kilojoules. So just like when we did with stoichiometry from your last chemistry class, enthalpy can be included as a part of the chemical reaction, and we would just write it after. So then I can start with the value I have. I start with 4.5 grams of methane, and I want to find out how much heat is released. So I need to know the value of the energy in kilojoules. And I know it's kilojoules because the energy is measured, enthalpy is measured in kilojoules. So first thing we're going to do is we have grams of methane. Hopefully your brain says, okay, 5 grams, I want to go to moles. So I'm going to use a molar mass of methane, which is 16.0 grams per mole of methane. Now you're like, where do I go from there? Just like we did with stoichiometry, I could say 1 mole of methane equals negative 890 kilojoules per 1 mole of methane. And then I'm in kilojoules. So that's it. We could actually just use our enthalpy as a form of stoichiometry. When you calculate that value, you end up getting that the enthalpy of this process, so the amount of heat that would get released, is negative 250 kilojoules. Okay, we have another problem down here where we have hydrogen peroxide decomposing into water and oxygen. It's balanced, looks good. Here's the enthalpy for this reaction. I want to calculate the energy released when 5 grams of hydrogen peroxide decomposes. So I want you to pause and hopefully try this on your own. I'm going to start now. So we are in grams. Similar to before, we're going to go from grams to moles. So we're going to calculate the molar mass of hydrogen peroxide, which is 34 grams per mole. And then I could use, for every 2 moles of hydrogen peroxide, I have negative 196 kilojoules. So again, use the coefficients. It's not always going to be 1 mole down here. It's whatever is in the chemical reaction for that substance. And that's going to give you negative 14.4 kilojoules. Or, and when you're doing your homework, the platform in Pearson might want you to, it might already say it might say the number and it will say released, like kilojoules released. That released is implied by here. So if you put negative 14.4 here, maybe it'll take it, but if it doesn't work, just try putting 14.4 because that released portion that they put there means it's implied that it's a negative. The rest of chapter 5 will all be about different ways that we can determine the enthalpy of reaction. There are going to be 5 different ways to find the enthalpy of reaction. Just a heads up, we're going to study calorimetry. In section 5.5, we're going to study Hess's law. In section 5.6, we're going to study enthalpy of formation, or delta HF, in 5.7, and then lastly we're going to do bond enthalpies in 5.8. Enthalpy in 5.8. So this is the rest of the chapter with those 4. So starting with 5.5, calorimetry is a way that we can determine the change in enthalpy of a reaction. Since we can't know the exact enthalpy of the reactants and products, we find that change through heat flow. So what we use is something called a calorimeter. And maybe you've already been like, oh, calorimetry, oh, calories. That is something that is related. And if you've taken a food science class, then you maybe have done this because calories are a form of energy. So to do this, basically the setup is we have 2 styrofoam cups that are tucked together, and the styrofoam cups are tucked together in order to provide insulation. And we know that insulation makes it so heat cannot escape. And then you have your reaction happening in there. It could be a reaction with water, a reaction where you mix 2 different things together, 2 different aqueous things together, substances. You also put a lid on it to help, again, prevent heat from escaping. You have a stirrer to help mix the solution and a thermometer. So, one thing you want to keep in mind is a topic called heat capacity. This is an intensive property of a certain substance. And the definition is the amount of energy it takes to raise the temperature of that substance by either 1 Kelvin or 1 degree Celsius. The specific heat is a little different because it's specific to the mass that you use, and that is the amount of energy it takes to heat 1 gram of the substance by 1 degree Celsius. So it really tells you how easy or challenging is it to change the temperature of your substance. If you've ever tried to boil water, you know it takes a long time. It takes a lot of energy to heat up water. But something like aluminum or some other types of metals, maybe you put a pan in the stove, immediately it becomes very hot, and that's because metals have a very low, very low heat capacity. And so when you have a low heat capacity, and the symbol is C, when you have a low specific heat, that means it's easy to change the temperature. When you have a high specific heat, or high C, that means it requires more energy, so it's harder to change the temperature. So water is an amazing liquid and substance in general because it has a very high specific heat, especially in the liquid form. It takes a lot of energy to change the temperature of the solution. So We also want to keep in mind the surroundings versus the system here. So when we have our calorimeter set up, our thermometer is measuring the temperature of the solution. So we know if I had an exothermic reaction, then my reaction, or my system, released energy. So it released some heat, meaning that it would have a negative value for the heat. When I have an endothermic process, then our reaction gained heat, meaning we have a positive value for the heat. So that's what's happening with the reaction. But when we measure it with the thermometer is measuring the solution. So let's think about the exothermic situation. With exothermic, heat got released. So if I was to measure it with a thermometer, me, the surroundings, then I would see that the temperature of my surroundings would increase. So that's the temperature of my thermometer. So here, if I have an exothermic process happening in my cup, let's just pretend that dot is my reaction that's happening, then I'm emitting heat. Temperature is going up. But when I'm thinking about the reaction value, the temperature of my reaction actually dropped because there was a transfer of heat. So the equation involving heat is that the heat involved of my solution, which I'm going to also put is the surroundings, what we measure in the lab, is equal to the specific heat times the mass of the solution times the change in temperature of that solution. But what we're measuring as the surroundings, if I want to find the enthalpy of, or the heat of my reaction, I'm going to need to change the sign, because the heat that my reaction lost is going to be equal to the heat that my solution gained. So they're the same value, but a different sign. And then I also want to make a quick little aside, because we know that enthalpy is related to heat. Enthalpy values, delta H values, are measured in kilojoules per mole of reactant. So what we're going to need to do is take our enthalpy of our reaction, divide it by the moles of our reactant, or whatever it tells you in the problem. So keep that in mind when we move forward. So let's do a practice problem. How much heat is needed to warm 250 grams of water, which is about 1 cup, from 22 degrees Celsius, which is room temperature, to 98 degrees Celsius, which is near its boiling point in Salt Lake? So we're going to calculate the heat involved in our solution here is going to be equal to C times the mass of the solution times the change in temperature. So we're going to plug it in. The specific heat of water, which is what we are heating here, is 4.18 joules per gram times Kelvin. And I'm also just going to get used to saying degrees Celsius, because our delta T could be degrees Celsius or Kelvin. I'll show you right now. Our mass of our water is 250 grams. And then our delta T, we started at, so it's final minus initial. Our final that we're ending at is 98 degrees Celsius minus 22 degrees Celsius, what we started at. So then we're going to multiply that all together, and you end up getting 7.9 times 10 to the 4 joules. Now, one thing I want you to think about is this delta T. So we went from 22 to 98. So that delta T is 76 degrees Celsius. Let's find the delta T in Kelvin. So what we're going to do down here is take my 98, I'm going to add 273, and then I'm going to do my 22 and add 273. So what you get is 371 Kelvin and 295 Kelvin. So we always want to change our temperatures first before we do the math. Then if I found the delta T between that, I'm just going to subtract the two. And when you subtract those two numbers, you also get 76 Kelvin. So as long as it is a change in temperature, you can switch those units between Celsius and Kelvin. If it's a absolute value, so a single digit, you just want to do your adding 273. So let's do a calculation of an actual chemical reaction. So we have a student, and they're going to mix 50 milliliters of a 0.1 or a 1 molar hydrochloric acid solution and 50 milliliters of a 1 molar sodium hydroxide solution. And here's the chemical reaction there. The temperature increases from 21 to 27.5. Calculate the enthalpy change for the reaction in kilojoules per mole of HCl. So that's what we want down here. We want the delta H of reaction in kilojoules per mole of HCl, which means we're going to need to get moles of HCl. Assume the calorimeter only loses a little bit of heat, and the total volume of the solution is 100 milliliters. Its density is 1 gram per milliliter, and its specific heat is basically water. So we're making a lot of assumptions here, but that makes sense. 100 milliliters is our total solution. One thing we want to do is make sure when we do our Q equals Cm delta T, we want to make sure we're using the total mass in our solution when the reaction is happening. So we know that we have 100 milliliters here, but we need the mass. So we get to use the density up here to convert into grams. So we know that we have the density of 1 gram per milliliter. So we have 100 grams of solution. It told us that we had a specific heat of 4.18 joules per gram degrees Celsius. I'm just going to straight go there so I don't have to do additional math. And my temperature got all the way up to 27.5 degrees Celsius, and it started at 21.0 degrees Celsius. So let's find the heat of our solution. Don't forget that this is our solution. So that's our first step here, is calculating that. So what we end up getting, that our heat of our solution is 2717 joules. All right, so we're almost there actually. We want the heat of the reaction, so we need to find the heat of the reaction. We just found the heat of the solution. If you remember from the other slide, so this is step 2, is you're just going to change the sign. So we're going to say equals negative 2717 joules. So that's one step. So heat of the reaction is 1. We also need to go into kilojoules. So I'm just going to do that right here. Step 3, I'm going straight over to kilojoules. So 1,000 joules per kilojoule. So we have that our heat of our reaction is negative 2.717 kilojoules. And then our last thing is to get it per mole of hydrochloric acid. It told us what mole to use. So what we're going to do here is use our volume and our molarity of hydrochloric acid to figure out the moles. So I'm going to do this over on the side here. So we have 50 milliliters of HCl. We need to get it into liters, so we could use molarity. 1,000 milliliters is 1 liter. And then remember that 1 molar is 1 mole per liter, so it's a conversion factor. So we can now go 1 mole per liter. So we do those calculations, and we end up getting that our amount of moles of hydrochloric acid that we added was 0.05 moles HCl. So now we're going to bring that down here. So for step 4, we're going to use the fact that enthalpy of reaction is equal to heat of the reaction divided by moles, in this case, moles of HCl. So we'll do negative 2.717 divided by the amount of moles, of kilojoules divided by 0.050 moles of HCl. So all of our units are correct. We are doing the reaction, we're in kilojoules, and we're in moles of HCl. So we plug in all of that math, and then our enthalpy of reaction is equal to negative 54 kilojoules per mole. We're going to practice again because there are many steps. So just to review, our first step is plugging into Q equals CM delta T. Our second step is then changing the sign, going from the heat of the solution to the heat of the reaction. Our third step is then going from joules into kilojoules. And then our fourth step is converting to moles, or finding the moles of our reactant, and then plugging into this equation here. So a few different steps. I want you to get comfortable with doing them. I feel like step 1, 2, and 3 are pretty straightforward. 4 is not too bad either, but we just gotta remember the sequence. So let's practice again. We have 100 milliliters of a 0.1 molar of silver nitrate and 50 milliliters of 0.1 molar of hydrochloric acid are mixed in a constant pressure calorimeter. The temperature of the mixture increases from 22.3 to 23.11 degrees Celsius. The temperature increase is caused by the following reaction. So we have our reaction here, 1-to-1 all the way across. Calculate the enthalpy of reaction in kilojoules per mole of silver nitrate. If the combined solution has a mass of 150 grams and the specific heat of 4.18 joules per gram degrees Celsius. So it could be very easy to just plug in to find the moles of silver nitrate by just plugging that in. But there's going to be another extra step we're going to have to do, and it's tied to something you've already learned. But let's get started on our steps that we know. Let's start with step 1. Step 1, we know that we have to do Q of the solution is equal to Cm delta T. So it told us a bunch of this already. We know, that the heat of the specific heat is 4.18 joules per gram degrees Celsius. My mass, it told me, is 150 grams, because 50 milliliters plus 100 milliliters with the density. And then delta T, we're going to go, it ended at 23.11 and it started at 22.30 degrees Celsius. So plugging that all in, we end up getting a value of 508 joules. So our Q of our solution is 508 joules. Now, if you remember, number 2, we are going to say that Q of the solution is equal to negative Q of the reaction. So if I want the heat of the reaction, which I do, then I'm just going to change the sign, negative 508 joules. So my solution got warmer, it heated up, meaning my reaction lost that energy. Third step, converting that value. So heat of my reaction, I need to get it into kilojoules. Under negative 508 joules, go straight into kilojoules, 1,000 joules per kilojoule. So we get negative 0.508 kilojoules. All right, the last step, which usually can be pretty straightforward, but in this case it's a little trickier, which I made it that way actually intentionally. So as a review topic, so we're mixing 100 milliliters of silver nitrate and 50 milliliters of HCl. So even though we have more volume of silver nitrate, we need to figure out when does the reaction actually stop. Because if I have extra silver nitrate that didn't get used up, it's not going to be part of the reaction. So what we need to do is figure out the limiting reactant. So I'm going to go over to the side here to do that. We had 100 milliliters of a 0.1 silver nitrate solution, and we had 50 milliliters of a 0.1 this would be molar hydrochloric acid solution. So let's find out how many moles there are of each and convert to a product to see who the limiting reactant is. So I'm going to start with this one. We start with our volume, 100 milliliters, and I'm going to go 1,000 milliliters per liter, and then I could use my concentration to do 0.1 moles per liter, and I am in silver nitrate. So now I'm going to convert between moles of silver nitrate to moles of, let's do silver chloride. It doesn't really matter, but we're just going to pick a product. Now the ratio is 1 to 1, so we can find out that the amount of moles we have of silver nitrate is 0.01 moles of silver chloride from that silver nitrate. Let's do the same thing with the hydrochloric acid, 50 milliliters of it. We're going to go to milliliters to liters. Same concentration. It won't always be, so this is why it's good to practice. 0.1 molar. And then we also have, we go to our reaction, 1 mole of HCl for 1 mole of the silver chloride. Okay, so plug that on in and we get 0.005 moles of silver chloride. So if you remember, this means that our hydrochloric acid is our limiting reactant, so not all of this 100 milliliters is going to react, so we need to find out how much will. So we'll start with our limiting reactant, 50 milliliters of HCl. And we're going to go to moles, so 0.1 molar. And then we get to go from moles of HCl. 1 mole of HCl is 1 mole of silver nitrate, meaning that 0.005 moles of silver nitrate are actually reacting. So that is very good to know. That actually solves it for us. So we can move that over to step 4, which is figuring out the enthalpy of our reaction, which is equal to the heat of the reaction divided by the moles, in this case, of silver nitrate. So we'll do our negative 0.508 kilojoules here divided by 0.005 moles of silver nitrate. So let's plug that in. And we end up getting a delta H value of negative 101.6 kilojoules per mole of silver nitrate. So this was just a review over here about limiting reactants, but keeping in mind we do want to find out who's limiting, who's excess, and if we have excess, we don't want to use all of those moles because they all didn't get used. We only want to use the amount that actually reacted. Chapter 5.6 starts with the definition of state functions. A state function is a type of property that depends only on the present state of the system, not the path that it took to get there. So you can kind of think of this as if I was to climb a mountain, right? If I was to hike up a mountain, there are different ways I can go. I could just hike straight up, or I could do like switchbacks, right? The amount of distance I took to go, those are not state functions, because if I chose path A here, where I just went straight up, that distance I went is not equal to the amount I took here. But if I wanted to consider something like the altitude is a state function. The altitude I gained from taking path A is equal to the altitude I gained from taking path B. It didn't matter the way I got there, I still gained that much altitude. So that's a state function. Change in energy is a state function, but heat and work are not. So for example, if I have a battery, there's a certain amount of potential energy stored in the battery. If I just connected it in a circuit, then there would be no work that got done. All of it would just, eventually that battery would get drained through the loss of heat. So if I have a charged battery, I could lose all of that energy through heat if I wasted it like that. Or if I plugged it into an appliance such as a fan, it would do some work, right? The electrons in there would power that fan, and some work would get done, as well as that the fan would also, this process would also involve some heat. You would know this if you've ever had your phone on for too long or your computer on. It gets warmer, right? So that's heat loss, and it is actually technically draining your battery a bit. So the amount of internal energy stored in the battery, it doesn't matter if I waste it all in heat or heat and work or all work. It's going to be the same, doesn't matter the path, but heat and work are not state functions. It does matter the path that they go on. So enthalpy is also a state function, which makes the next process really nice. So we're going to talk about a topic called Hess's law. This is another way that we can determine enthalpy of reaction. So in a lot of different tables, the enthalpy of reactions have been measured and tabulated. So they are listed in books and tables that you can find online for lots of reactions. But it's not possible, and it's pretty inconvenient to measure every single enthalpy for every reaction that's out there. So we need to be able to do something else. So what we can do is actually use the published enthalpy values that have already been determined experimentally and mess with those reactions, manipulate those reactions in such a way that we can calculate the enthalpy value of a reaction we're interested in that doesn't have a tabulated value. So what we're going to do is learn what Hess's law is and then practice it. So Hess's law says that if I have a reaction that's carried out over multiple steps, then the overall reaction is equal to the sum of all of the individual steps. So over here on the side, we can see a reaction we saw earlier. We saw the reaction of methane reacting with oxygen to produce, we actually saw this one down here, liquid water and carbon dioxide gas. But with the process that takes is, it takes 802 kilojoules get released when this reaction happens and the water is in the gas phase. But another reaction happens between water going from the gas phase to the liquid phase. Another 88 kilojoules is released. So we can take these two steps here, this 802 and this negative 88 kilojoules, and add them together to get our desired reaction, which is this one. So we can do this because enthalpy is a state function, so it doesn't matter the path that the reaction takes to get there. I could do it in 2 steps, or I could do it in 1 step or 4 steps. As the enthalpy value is going to be the same for that reaction that I'm interested in, no matter what path it takes. So let's practice. What's going to happen is you're going to get a series of reactions. So here we have 2 reactions that were given. Notice these have enthalpy values that have already been determined. So those we'd maybe find in a textbook or online. And then it says, using this data, calculate the enthalpy for the combustion of carbon to carbon monoxide. So this is our goal. This is what we want to find. And we do not touch our goal. We are leaving our goal in place. What we're going to do is manipulate our reactions up top, those steps that have already been determined, in a way to get this reaction that we want. And I just want to make a quick note that I forgot this half here in these notes, so make sure you have those on yours. Anyway, so we're not going to touch our goal. We are trying to find it. We're going to manipulate these other reactions to get it by adding them together. So my recommendation is to hit up every element or chemical from the left to the right until you have used up both of those reactions that we are given. So I'm going to start with carbon here. I'm going to go find carbon in these two reactions and manipulate it to get it. I want one carbon to be a reactant for my goal. So I'm going to go find it. I can see that I found carbon right there. If you look at reaction number 2, there's no carbon by itself. So I'm going to rewrite reaction 1. Now, looking at our goal, we want one carbon and we want it to be a reactant. And we have one carbon in number 1 and it is reactant. So this one is actually good as is. I'm going to write it anyway. Carbon plus oxygen goes to carbon dioxide. And the enthalpy value for that is negative 393.5 kilojoules. Okay, now I'm going to go over to our second one. Here I have oxygen. Now I already used reaction 1, but notice oxygen is there and there in both reactions. I actually want to stay away from elements that show up or compounds that show up in more than one of these steps. So I'm going to stay away from that. For now, let's actually now look up carbon monoxide. So carbon monoxide, if we look at that, it shows up in the second reaction as a reactant, and I want it to be a product. So I'm going to flip reaction number 2, flip it. So I'm going to write carbon dioxide as a reactant, going to form carbon monoxide gas and a half of an oxygen. And then the enthalpy for that reaction is going to be the opposite sign. So if I flip a reaction, I'm going to flip the sign. It's going to be positive 283.0 kilojoules. So now what we want to do is add up the reactions as well as the enthalpy values to see if we get our goal, which we should. So we have carbon on our reactants as a solid. We have carbon dioxide showing up as a reactant and a product. So it actually cancels out, which is good because it's not in our goal. We have one oxygen on our reactants and a half an oxygen on a product. So we're going to look at the net amount of oxygens we have. One reactant and a half a product means I have a net reaction or a net amount of oxygen of a half oxygen as a reactant because there's more on this side. And then I have carbon monoxide gas. So we check, does that look like our goal? Yes, it does. So the value for that, now we're just going to add up these enthalpy values. So we're going to add negative 393.5 plus positive 283.0, and we get our enthalpy of this reaction to be negative 110.5 kilojoules. Okay, so that's the process. You figure out what your goal is. It's the one that you don't know the enthalpy for. You then manipulate your steps that you're given to find your goal, and you're going to start from the left to the right and go search for those elements, and if they show up in more than one reaction up here, you're not going to use it. All right, let's look at this next one. We want to calculate the enthalpy for the reaction 2NO plus oxygen goes to N2O4. So this is our goal. Okay, so make sure you know what your goal is. And we're going to just start from left to right and figure out what our enthalpy is. So here's step 1 and step 2. So I'm going to actually write those right there. So we're going to start with our reactants. We're going to look there. We have nitrogen monoxide. Now notice I only have nitrogen monoxide showing up in number 2 here. So step 2. And I want a 2 in front of it, and it has a 2 in front of it, and they're both reactants. So we are good on this one. I have 2 NOs plus an oxygen goes to 2 NO2, and that delta H is negative 113.1 kilojoules. So number 2 is done. Keep in mind, once you use a step, you don't use it again. It's done. Now I'm going to take a peek at the next one. I have oxygen. We have oxygen there, but notice we already used that oxygen, so I'm going to move on to the next one, dinitrogen tetraoxide. I want it to be a product. I'm going to go find it. It's in number 1. Here it is. I want 1 in the front, but I want it to be a product, so I'm going to flip this one, and I'm going to change the sign. So I'm going to do 2 NO2s goes to N2O4, and the delta H for that is going to be negative 57.9 kilojoules. So when we add all of that together, we get, notice what cancels out. We have our nitrogen dioxide cancels out. We end up getting 2NO plus oxygen goes to N2O4. Add up those enthalpy values, and we end up getting negative 171.0 kilojoules, which is D. And lastly, another practice problem to do Hess's law, because I do know that it does take students a little bit of time to figure it out. Sometimes it feels a little scary, but to me it kind of feels, now that I know what to do, it feels kind of like a game or like a puzzle. So calculate the enthalpy value for the reaction. 2 carbons plus 1 hydrogen goes to C2H2. So this is our goal. We're going to start with our 2 carbons. So let's go find carbon. The first reaction doesn't have carbon by itself, but the second one does. So we want it to be a reactant, but we want it to have a 2 in front of it. So what I'm going to do is multiply that whole thing by 2. And also, we're going to multiply, whatever you do to the reaction, you have to do to the enthalpy. So we'll get 2 carbons plus 2 oxygens goes to 2 carbon dioxides, and my enthalpy value is going to be negative 787 kilojoules. All right, so first one is done. Now let's look at the next chemical. We have hydrogen. I do not see hydrogen in that first reaction, but I do see it in the second. Is a reactant. We want it to be a reactant, and they both have 1 coefficient. So we'll write that just how it is. H2 plus O2 goes to H2O, and delta H will stay the same. Okay, and then lastly, we have our C2H2. It must be in the only reaction that's left, which is number 1. We want it to have a 1 coefficient in front of it, right? And then we want it to be a product, so we need to flip this reaction, which means we're going to change the sign of this guy. So we'll end up getting 2 CO2 plus water goes to, all right, I just actually looked at my notes. We have some missing numbers here. So there is a 5/2 in front of this one, and there is a 1/2 in front of this. So I'm actually going to put that 1/2 in here. And then when I go to write this next reaction, I can do 2 carbon dioxide plus water goes to 5/2 oxygen plus C2H2, and my delta H value is going to be positive 1299.6 kilojoules because we changed the sign. So we're going to add it up. Let's see. Does anything cancel? Well, I can see already carbon dioxide and carbon dioxide. I see 1 water and 1 water. So this is where it gets a little tricky. I see 2.5 oxygens, and 5/2 is 2.5. So we actually cancel out there. All right, so what we get is 2 carbons plus a hydrogen goes to C2H2, and that was our goal. So then we add up those enthalpy values, and we get our delta H of the actual reaction we are interested in, being 226.8 kilojoules. Okay, this is the end of this section.